Okay, welcome back to the class meeting. This is 14th class meeting. So last time we've seen something very interesting about the improper complex random processes with period capital T. And at that time, I draw two bispectrum. One is derived from the ordinary autocorrelation function of the random process, and the other was from the complementary autocorrelation function. So let's start with that point. So we had the properizing fresh vectorizer and scalarizer looked like this one and that one. So let's take a look at this structure again. The key difference between the ordinary fresh vectorizer from p-fresh vectorizer is that we have here the low-pass filter that actually filters on the passband ranging from 0 to 1 over 2t. So 0 to 1 over 2t is the passband of these filters denoted by g of t, its impulse response g of t. So however, still the adjacent frequencies, neighboring frequency values are 1 over t hertz apart. What does that mean? So in the upper branch, not all the signal components, but only around half of the signal components passes through these filters. And also, after conjugation, the other half of the signal components, in this case y over t, filters through this lower part of the branches. Got it? So we have twice the length of the ordinary fresh vectorizer in this p-fresh vectorizer output. And what we are going to see is that we take a look at the correlation between each component or each element of this vector valued random process. And if you take one from the upper part and the other also from the upper part, then we correlate the components on, where it is, yeah, on these lines. So let me mark them. So for example, this one, that one, that one, that one. So within the kind of square Nyquist area, only this northeastern part of the delta function's height is obtained by correlating two of the upper branches. What about correlating the lower parts? So you take one here, the other here, something like this. Then you fill up that part, and that part, and these parts. What about you take one from the upper part and the other from the lower part? In that case, since you have conjugation, actually you cannot put that information here in the ordinary bispectrum, which is the double symplectic Fourier transform of the ordinary autocorrelation function. You can only put that information on the height of this symplectic Fourier transform of the complementary autocorrelation function. So in that way, you get the information on the heights of these impulse fancies. Got it? So when Dr. Byung-Woo Han and I finished this work, we still had some difficulty to fully understand the secret in the improper complex cyclostationary random process with cycle period t, because still, even though this properizing fresh vectorizer is an invertible, not this one, scalarizer, this properizing fresh vectorizer is an invertible transform and contains all the information in y of t. And after the conversion, this capital Y of t becomes proper y-sense stationary vector random process. And we also could derive the capacity of cyclostationary Gaussian noise channel and show interesting results, some numerical and some analytical results like this. But the secret was not fully revealed. So we continue the research now with Dr. Jung-Ho Yeo and found another interesting property of this improper complex cyclostationary random process with period t. So let me give you what was the surprise in this paper, which appeared in the IEEE Transactions on Information Theory. So as you see, some important results are really publishable in more prestigious journals. Sometimes we have bad luck, so that journals happen to be selected reviewers didn't like our work and didn't highly evaluate our work. In that case, we submit the work again to other journals. And at that time, submitting some rejected paper to a different journal was not a problem. That was a common practice. However, during last 2 decades, number of publications in our area dramatically increased, quadrupled, probably 8 times, 16 times, something like that. And then people try to put some constraints like if your submission is previously submitted and rejected, then you have to mark what was the title of the journal and what were the reviewers' comments, and you must respond to the comments. So it's like you are still haunted by the reviews of the previous journal submissions. So that is has become a common practice in many of, not all, but many prestigious journals. Especially signal processing society journals really have this very, very strong requirement. So it's like, even though you submitted your original work to IEEE Transactions and Communications, which is operated by IEEE Communications Society. For example, you got rejection and you submit it to IEEE Signal Processing or Wireless Communications, which is cooperated by Communication Society and Signal Processing Society. In that case, you have to list up all the previous review comments and your responses. So it's like publication, how they said, hell is has come to the researchers. So it now has become very important to cut through the review process just in one try. Otherwise, you have very, very, very difficult time to get your work published. However, some societies still don't have that kind of restrictions. So in that case, your rejected work can be still submitted as a new one. And I think that must be the practice, because sometimes you will see when you submit your work to journals, sometimes the 2 out of 3 reviewers are very prejudiced, or even do not read your manuscript carefully, but have very, very strong opinion. In that case, it's impossible to respond to their comments, because their comments would be totally technically wrong. How can you respond to technically incorrect comments? Anyway, and this paper was very lucky to pass the review process. Anyway, because it contained very, very interesting, strikingly new results. And what is that? Simply put, a second order improper complex cyclostationary random process with cycle period T is equivalent to a second order proper complex cyclostationary random process with cycle period 2T. So this is the surprising discovery found through this work. So before, we divided a set of second-order random processes into some stationary, some cyclostationary, blah, blah, blah. So suppose you have the set of all second-order cyclostationary random processes. Then, as you know that you can divide the set into 2 disjoint sets. One is proper, and the other is improper. However, this work shows that impropriety can be viewed as propriety after you perform some invertible transform. Here, the equivalence is established by proposing an invertible transform. For example, fresh vectorizer is an invertible transform. Properizing fresh vectorizer is also an invertible transform of a second-order random process. Here, we propose so-called fresh properizer. And its input is, in most of the cases of interest, improper complex random processes, and output is proper complex random processes. And you may say that, hey, we had the same situation when we studied properizing fresh vectorizer. In that case, the difference is that now here you put scalar valued random process x of t, and here you have again scalar valued random process y of t. In properizing fresh vectorization, you had a scalar valued random process, but in the output you had the vector valued random process. Vector y sense stationary, and also vector proper random process. In this case, you have scalar valued random process in and scalar valued random process out. And what kind of transformation occurs in this fresh properizer? And that's very, very interesting. And again, very closely related to what you already know. And when I talk about the spectral correlation in improper complex random process, I told you something like this. Suppose you have some real valued signal, S of t, and what's the property of its Fourier transform? And its Fourier transform has conjugate symmetry, right? And this result is very, very similar to what we are going to see. So in the previous work, what we did was that instead of slicing the frequency band into lengths 1 over capital T, in the P properizing fresh vectorizer, we divided into what? Lengths 1 over 2T, right? And we collected this part, this part, this part, and so on for the upper part of the P-fresh vectorizer and the other part in the lower part. And motivated by this idea, what we do here is that we just flip the frequency content in this interval. So what we are going to do is that we are going to propose an invertible transform that effectively flips, moves the frequency component here to there, and for example, there to there. So within this interval, with the center frequency as the kind of point of symmetry, we are going to flip the frequency components. And let's see what happens. Why do we do this? So the story is like this. Suppose you consider some f0 between 0 and 1 over 4t. And before, when I talk about improper complex random processes, this frequency component not only correlated with, not that one, sorry. These frequency components with integer multiple of 1 over t hertz apart, also they are correlated with what? These frequencies, right? Just a second, not that one, this one, and that, right? So negative f0 component and positive f0 components are correlated, similar to what we have in the conjugate symmetry of the Fourier transform of real valued signal. Ready? So let me show you what we did here. So now consider a little bit different impulse response from what we've seen in the previous paper. In the previous paper, we only had this passband, right? This was the only passband before, but now we have other pass subbands. So these pass bands put together are related to that upper part of the P-fresh vectorizer, right? And now this filter with impulse response G sub M is now, for example, this is discrete time version, but we can have a continuous time version. So we have x of t, and here goes the conjugation operator, and here goes G sub M, not only M, G sub in this case. Yeah, let me be careful. Yeah, T. No. Yeah. Notation should be different. Just a second. Here, in this paper, we only consider discrete time random process, but we may have continuous time version. And in that case, let me just use G tilde. Got it? Now, let's see what is the output. So what we assume is that in the continuous time case, G tilde of F has passbands like this. Got it? So this x1 of t is what? Is the component of x of t on this subbands, right? Now, in the lower branch, what do? Just think about Fourier transform of a finite energy signal, even though we are not handling none of them. So conjugation means what? As I've shown you, what you do is that you conjugate the complex gain of an exponential signal, and also you flip, right, the frequency. So the simplest way is to consider taking the conjugation of it, that is A conjugate e to the negative j, a positive j 2 pi negative f0t. Got it? So after flipping, what happens? Those signal components on these stop bands now at this point appears in the pass bands of G tilde. So this lower part contains the other ones. The difference is that some frequency component that was originally here is now what? Appears, since you flip, there, right? And some frequency components there now appears what? Here, something like that. So actually, unlike what I just told you, that was just flipping that way. Actually, that is one method of properizing. But the simplest one is just you put conjugation and put G tilde. Then what happens? As I told you, this one now appears there. And here we again have arbitrary choice. We just shift down. So here we have e to the negative j 2 pi 1 over 2t t. Got it? So take a look at this. Some signal component here flips here and shifts down back to here. Got it? And of course, you may do some change there. Instead of 1, you may choose 3, 5, 7 if you want. But this choice makes kind of, how to say that? If this is the center frequency, then you do this and shifts something like that. And you add up to have a scalar random process. So if you just take a look at the frequency contents, the frequency content of this one is all the frequency contents is contained here and vice versa. Got it? Now, what's the property of this y of t? Is it proper? Is it y-sense cyclostationary? If so, with period what? And this paper for the discrete time case shows that what I claimed here is true. Got it? So by using such an invertible transformer, you can transform an improper complex Weiss-and cyclostationary random process with period t into Weiss-and proper complex Weiss-and cyclostationary with period 2t. And it somehow makes sense if you just remind the spectral correlation, because what you have is something like this. So before, the frequency component at here and here and here were correlated, and they were 1 over t hertz apart, right? And also, you had the spectral correlation with this and that one. Now, this component is moved to here, and this way, you can show that you have correlated components at the output of the fresh properizer. Now you have what? 1 over 2t. What does that mean? If you have spectral correlation, with integer multiple of 1 over 2t hertz apart, then what? Your cycle period of the cyclostationary random process is 2t. Got it? So that justifies this part. And what about this one? And you need some proof. And what you need to do is that you compute the complementary autocorrelation of y of t and show that it vanishes. And that is really true. Got it? And by the way, as I told you, there are many different ways to properizing and also doubling the cycle frequency by choosing different frequency shifts in the fresh properizer. And this structure is chosen just for simplicity. You may really choose each half Nyquist zone and just flip the frequency components with respect to each half Nyquist zone's center frequency. In that case, your properizer would be more complex, would have more complex structure. So just conjugating and then little bit shifting up or down, not too much, would be the simplest method to properizing the improper complex cyclostationary random process by doubling its cycle period. Okay, so this is the basic idea. And here comes why then we considered discrete time random processes in this paper. And there are many reasons we have chosen this one. And interestingly, one of the minor, but one of the obvious reason why we didn't consider continuous time random process is that first, we published that part in a conference paper. And we needed to put more results in the journal version, and especially we wanted to submit it to this transactions and information theory. Unfortunately, Dr. Jung-Ho Ye and I found that working with continuous time random processes, we just have almost the same set of problems like Okay, then what is the capacity of cyclostationary Gaussian random process channel with cycle period t? In that case, we will have same results, something like that. And also, I didn't show the other set of research work in my group that my former graduate students had developed the results related to the block transmission with cyclic prefix or zero padding or unique word throughout around a decade of work. At that time, we showed that asymptotically, which means that if we have large enough, for example, FFT point, then we have some convergence, blah, blah, blah. So we wanted to make that part, especially where we assumed only proper complex interference and data-like interference. But here, to extend those results to improper case, we considered discrete time cyclostationary random processes. So as you see here in many of the equations, we have again defined the mean path autocorrelation and complementary autocorrelation function for discrete time random processes. And also we have spectral correlation function or complementary spectral correlation function you may call bispectrum and complementary bispectrum by doing discrete time Fourier transforms, symplectic Fourier transforms, and discrete time Fourier transforms applied to each auto and complementary autocorrelation functions. And we have the definition of second-order stationarity and second-order cyclostationarity. You may just assume that it's a little bit different from Weiss and cyclostationarity because these definitions involve complementary autocorrelation functions. Got it? And here goes the lemma. We already developed for continuous time cases. Now for discrete time random processes, you've seen similar results in your first take-home exam. And here again, we have impulse fences appearing in the bispectrum and complementary bispectrum. The difference is that, as you remember from discrete time Fourier transforms, what do you have? You have automatic periodicity of spectrum. So in these two functions, what you need to focus on is what? In terms of hertz, probably only this square area, because what? Because of the periodicity of the Fourier transform. 2D Fourier transform or symplectic Fourier transforms does not differ when we consider discrete time Fourier transforms. As you remember, given, for example, a discrete time signal, what is the discrete time Fourier transform? It's the product between the signal and complex exponential function with frequency f. And here, this, the complex conjugate of e to the j 2 pi f and e to the j 2 pi f plus some f0 and equals e to the j 2 pi fn if f0 is any integer. So it's periodic with period 1 when we consider the frequency in hertz, right? Similarly, even though you may evaluate this function at any combination, at any pair of f and f prime, let me use just f and f prime, but only this part does matter because they are all the same. Then the question is, where is our impulse fancies? And impulse fancies are all packed within this, inside this square for discrete time random processes. And if m is the cycle period, your impulse fancies are what? 1 over m hertz apart. So here you have impulse fans, and you know that this length is 1, so you divide that into m, then you have another impulse fans, another one, another one, another one, something like this. And these spacing are 1 over m hertz. Got it? So that's the difference. And some of you already noticed that when we introduce L and K here, even though we have infinitely many L, we have only M lines. So within this square, only capital 2M plus 1 lines we have. Got it? Center one and M of them and M of them, something like that. So that's the difference. So here goes the theorem that was striking results to many of the researchers who were familiar with the proper complex and improper complex cyclostationary random processes. So as you see that the output y of n, output random process, we assume the zero mean, so here we again have mean zero. But interestingly, the autocorrelation function is periodic with periodic, has period 2m, and m, capital M was the original cycle period. And here your complementary autocorrelation function vanishes. Got it? Okay, what is 27 proposition 1? Let me see. Okay, yeah, our conference version. So in the conference version, I remember, had probably the continuous time, is it? It appears that this is the discrete time version again. Okay. Yeah, probably we publish it, the continuous time version, in other conference paper. Anyway, so this shows the most important result. So theoretically speaking, whenever you have improper complex observation, there exists a processor that converts the signal to properize and does proper complex processing. Theoretically. However, really implementing that one could be very cumbersome. And actually, some of my former graduate students tried to realize such receiver for communication signals, and most of the results were not successful, unfortunately. So you may have interest in that, to this one. For example, let me give you an example. So suppose you have a BPSK signal. So here, B sub n is either positive or negative 1, and P is the transmit pulse, and theta is some, for example, non-zero signal. And you can easily show that the autocorrelation function of this signal is the complementary autocorrelation function of this signal does not vanish, which means that this BPSK signal is improper complex random process with cycle period capital T. So the question was what? For example, what happens we use fresh properizer to convert this one to a signal with cycle period 2t. Since this is proper, we can put some conventional receivers, of which theory has been developed for many, many years, and of which simplified algorithms are available in many literature. And unfortunately, in this problem, we haven't been so successful, unfortunately. We must have something very simple, but could not get one, unfortunately. So you think about it, got it? Anyway, in this problem, in this paper, so the problem was about some detection problem and estimation problems. So conventional statistical signal processing problems were tackled, not like data symbol detection problem in communication. And fortunately, this paper shows that this properizing method makes estimation and detection problems very, very simple. So here in section 4, application of fresh properizer. By the way, here, one of the reasons why we have asymptotic is that we have another one between the previous simple fresh properizer and the results. As I told you, in most of the cases, we use not a discrete time signal, but a vector taken from a discrete time random process. But its length is large enough. In that case, we process vectors, but we want to show that if our length of the vector is large enough, so for sufficiently large length, which involves the limit operation, then we have some convergence. And that is between that simple figure and this section. Anyway, so we apply the asymptotic fresh properizer to signal estimation problem, and if I remember correctly, signal presence detection problem. Not data symbol detection problem where we have many, many symbols. Got it? Anyway, in these two problems with very simple model, our asymptotic fresh properizer just showed that we may utilize the well-developed theory of proper complex signal processes because we already properized or almost properized the random process. Got it? Anyway, so here, as you see, that we have a lot of figures like this that's similar looking to the impulse fences. And actually, here, we take the length n vector. And what we do is that, so for example, we have discrete time signal, and here comes serial to parallel converter with length, for example, n, means we cut n samples and then n samples and then n samples to generate some vectors indexed by L. This is not the fresh vectorized output. This is simply serial to parallel converter. And then you process this vector by doing, for example, endpoint FFT. So this time domain signal now here becomes a frequency domain signal. And this frequency domain signal, if you take the correlation, then you have what? Then here you have correlation matrix of this frequency domain vectors, right? And interestingly, if this is cyclostationary, improper cyclostationary, then what happens? Your signal have two correlation matrices, which will have what? Will have some correlation matrix which is Hermitian symmetric and which is Hermitian anti-symmetric. And now let's take the magnitude of them, then what will happen? Interestingly, if you take large enough size n, then this one also has what? Has only those elements on this diagonal and off-diagonal lines have non-zero or far from zero elements, and all the other elements are zero, something like that. Here, the reason why we have this periodicity is that, if I remember correctly, due to some choice of n and m, that would contribute to the how many sub-blocks you have, something like that. Yeah, here, see that n equals 50. Let me see. Yeah, n equals 50. N equals 50. What does that mean? Yeah, what is n? Yeah, I believe m times n in this case is the length. So let me say mn. Got it? So mn. This is mn. Mn. Got it? So the length is chosen as an integer multiple of cycle period. So in this case, since m equals to mn equals 100, why we have 200? Yeah, so only this part does matter, I believe. Am I true? Oh, okay. I got what is wrong. Okay. So this is already after we properize the signal, I believe. Okay. Anyway, so we may apply something similar to this one. So we have x of n, and here goes fresh properizer, and we have y of n. Then we have serial to parallel conversion, and then we have FFT. Then we have properized signal here. So we only need ordinary autocorrelation of these vectors. And if the length of the vector is large enough, then as we increase the size, more and more terms become zero. and we have almost impulse fence-like autocorrelation functions in our matrix. In that way, our asymptotic optimality or properization is justified. So be careful. We have discrete time random process, and we take large enough chunk, and then we have a vector that can be claimed as a proper complex random vector asymptotically. So, which means that we can ignore complementary autocorrelation property of that vector because the improper components are almost gone. Got it? So this way, this paper showed something very, very interesting. So first one was this one, and this one is for continuous time case. And we move our interest to discrete time case and also vector case. So it's like you have three types of signals in signals and systems. First one is continuous time, and second one is discrete time, and third one is many cases describe discrete. For example, continuous time Fourier transform, discrete time Fourier transform, and discrete Fourier transform. And this continuous time Fourier transform is on a continuous time signal. Discrete time Fourier transform is on a discrete time signal. And this discrete Fourier transform is on a vector. Similarly, this paper not only talks about that theory and also extends our fresh properization to a vector random process that is obtained by just simply performing parallel to serial conversion. And many of you are familiar with OFDM, standard OFDM modulator and demodulator, where this type of parallel to serial conversion and serial to parallel conversion are common practices. In that case, in many cases, we may find some difficulty in connecting this vector valued signals spectrum, if you want, or frequency content with the original continuous time signals spectrum or frequency content. But anyway, relations between a continuous time, discrete time, and discrete signals are very important, and they are topics of digital signal processing, as you remember. From this conversion, continuous time to discrete time, what happens? You need usually uniform sampler. So you know what happens in this sampling, uniform sampling, spectrum folding. And then what happens when you move from here to here? There are basically two types of approach. One is just apply time windowing and to the discrete time signal and apply discrete time Fourier transform and find this relation between discrete Fourier transform, right? And another one is that you completely ignore relation between these two and take you are given a vector valued signal and you want to use some orthogonal basis that happens to be so-called Fourier basis. However, in many cases, the first approach is very common because we are communication engineers and we eventually want to work with continuous time signals. However, this point of view is also very, very important because these days, not only Fourier basis, but also other bases are finding more and more applications, not only in image processing, but also in continuous time digital signal process, digital communications. For example, in OTFS, orthogonal time frequency space modulation, people have found some interesting application of Hadamard transform. That is another, that provides another basis. And people also want to apply other bases that has been very popular in mostly signal processing, especially image processing. And most of them have the commonality in that they are unitary transforms, so energy preserving, and somehow they randomize the directions. That gives us some robustness in random channel, because some random channel removes some energy in a specific dimension, or puts some, amplifies some energy in a specific direction. And interestingly, information theoretically, that kind of putting some energy, removing some specific energy is very, very dangerous when we do not know what kind of channel will be realized. For example, we put all the power or energy of our transmit signal in some specific direction, and happen to be this channel nulls out that part. In that case, we lose a lot of energy or power that contains the information of our signal. So basically, our error control coding and modulations tries to uniformly spread our signal power as far as we don't know what will happen. Of course, if we know what will happen in a channel, we want to exploit the channel's property. That's why we do water filling. So in a better channel, we put more power. In a bad channel, we put less power. That is water filling. So be careful. Sometimes we have a lot of information about the channel. In that case, we may exploit the channel's selectivity. But in some cases, that is almost impossible. In that case, we'd better spread our energy through all the spaces. In that case, some non-physics motivated transformation. For example, in our world, we think in the frequency selectivity, this Fourier basis may be very dangerous. We may put some interference from this subband to that subband, then the data on that subbands are gone. However, within this band, we somehow spread out all our energy. Then if some interference kicks in this band, anyway, our energy is spread. So energy on this area will survive, something like that. So be careful. Anyway, so this paper has focused on discrete time and vector processing. And in order to link this discrete time and vector processing, we increase the size of this output of the serial to parallel converter. And we apply some asymptotic results related to random processes. So in this paper, we talk about almost sure convergence of a sequence of random vectors or something like that. Got it? So the idea is very simple. There are many different approaches, but the simplest one would be not using this discrete time filter that has very sharp edges. So what we do is that simply we have x of n, and here serial to parallel converter. And then we Fourier transform. And we have some lengths of vectors. And then we do exactly what this does. For example, we take this part, that part, that part, and that part, and that part, and keep it there. Instead, we take these parts And we flip as we do complex conjugation in the time domain. So in FFT, if you remember correctly, this is zeros component. So that one, the last one, has what? Relation with the first, correlation with the first, actually, if we start from zeros and first, right? This first and last have correlation. So what we do is that we move this one, for example, to the first line, or we move to that one, depending on which one is easier to implement. Got it? So this figure shows how we generate the results. Let me see. Yeah, so A is the Fourier transformed vector x. So here we have 1, 2, n over 2, n over 2 plus 1, 2, n, blah, blah, up to mn. And probably this is the upper branch output. So upper branch in this case, I'm not sure, but GMN, where is that? Yeah, where is the structure? Yeah, I'm not sure where it is. Yeah, anyway, yeah, see that? Yeah, something like this, if I remember correctly. No, that one. Yeah. So as you see that this one appears here, that one appears here after conjugation. Got it? And anyway, as I told you, we may flip it or we may just do this flipping, and it depends on which one is easier. And I do not quite remember what kind of flipping we introduced in this transformer. But the idea is like this. So, yeah. Okay, got it. So initially, this is the time domain signal, and this is the complex conjugation. So this is a standard technique in improper complex signal processing. Be careful. Unlike conventional improper complex signal processing, we also assume our vector is obtained by taking by the serial to parallel conversion. Probably you remember the book by Schreier and Schaff. So if you search improper complex signal processing, then I believe this is the, yeah. You see Schreier and Schaff's book, Improper Complex Random Process for Signal Process Communications. In that case, they start from improper complex random vector. The difference is that in our group, we also assumed cyclostationarity because that is so prevalent in digital modulation, and I'm a communication guy rather than a signal processing guy like Schreier and Sharp. Got it? But anyway, this augmenting method is a standard trick used in improper complex random vector processing. So we do something similar. And then this augmented signal is filtered. Got it? So that is the way we took in this paper. So there are, as I told you, there are many possible different methods to fresh properizing a random process, right? You only need to just flip or arbitrarily shift those frequency bands in -1/2t to 1 and their integer multiple of 1/2 Hertz shifted versions. You need to just take the conjugation and flip. Got it? So in this question, some clever, simple method could give you very good result. I haven't yet found, as I told you, given BPSK, which is definitely improper complex cyclostationary random process with cycle period T. Can we find some fresh properizer structure? As I told you, there are many fresh properizer structure that gives you a proper complex digitally modulated signal with cycle period 2t. Got it? Anyone? Anyway, so we have around 7 minutes, and I will give you more overview about this paper. So where do we have? Okay, so let me talk more about the linear receiver and widely linear receiver, because that is, as I told you, a common terminology in improper complex signal processing. So suppose now here we have a random vector x, and this is abuse of notation, but just forgive me. Suppose we have capital length capital L, complex improper random vector, no random process at all. Then people have developed this idea. You put the conjugation of it, so your vector is now length twice of the original one. And another one is that you just take the real part and imaginary part. So you convert the vector into length 2L real valued random vector. By the way, which one do you prefer? If you are more mathematician than engineer, probably you would prefer this one and would say that, hey, obvious, because a complex random variable is actually equivalent to length 2 to the real random vector. And this is exactly the idea. And if you just convert this one into that one, and you do processing, signal processing for real valued signals, like so you do some detection and estimation based on this signal of length 2L. Nothing new there is, right? You already know how to do this. However, people focused more on this one. Let me use Z here, okay? Because this Z is complex value. And one of the reasons why people do this is that electrical engineers are familiar with handling complex valued signals. Why? Because in radio communication, we handle real valued bandpass signals and random processes, and they have complex baseband equivalent signals. So our signals are already complex valued, and we develop all the modulation symbols and other filters in complex domain. And also, in most of the cases, the functions we develop to process the signals are analytic functions. So even though the input signals, input of the argument of function is complex valued, sometimes we just have a real scalar output, or even when we have two real values or one complex value output, we have each function analytic. Most of the cases. In most of the engineering problems, we have such property. So we want to keep using these complex valued signals. Then what is wrong with this approach? So it's like, suppose you have some channel capacity problem with complex input and complex output and some complex noise. And it appears that if you just augment the complex valued vector with its conjugate, then you have suddenly twice the subspace you can play with. Then is it really true? Something's wrong. It's like an alchemy, right? Yeah. Suddenly you have twice the space and twice the freedom. What's going on? So what you can do is that you may consider a Gaussian, complex Gaussian random vector that is improper. So suppose you have mean vector and you have some covariance and complementary covariance matrices. In that case, if you consider, sorry about this, X. If you consider Z that is length 2, then still you have complex valued 1, now with mean vector twice of its length, and you have some correlation and complementary correlation. And you will find that your degree of freedom does not multiply, but does not become twice. So what does that mean? If you view your signal in real domain, actually you don't have length 2L. Sorry. If you view the real and imaginary part of this one, then you have length 4L real valued vector that has what? Singular correlation matrix, which means that not all 4L components can never be independent. They have half of the space wasted. Otherwise, you have alchemy. So anyway, this one also has some problem when you handle that. You confront a lot of singular matrices. So I don't like actually this approach if our processor involves inverse matrix of large size. But most of the cases, the researchers circumvent that problem by, again, they block process this G of length 2L as we do here. See that? Even though we do some processing, anyway, we divide them so that we have some inversion of non-invertible matrix problem. We do not want to have that. Got it? Anyway, so yeah, you will see a lot of complicated inverse of inverse, something like that, right? Anyway, so let me wrap up after stating this one. So given a complex valued random vector, simplest and straightforward idea is to convert them to length 2L real and imaginary part vector. In that case, you have very, very simple, no trouble at all in doing some inversion or something. The problem is that your complex valued, for example, in communications, complex valued symbols may have very weird mapping to have that one. Many of you may say that, wait a minute, if we have a square com and if we apply natural binary decomposition, we have real and imaginary parts well separated. In that case, taking real and imaginary will have no problem. But actually, when we receive the signal, we have some unknown rotation of the constellation. In that case, what will happen if you take the real part and if you take the imaginary part? All these binary decomposed components will appear, not only this real part, but also the imaginary part, and they are just have very complicated mapping rules. So that does not work. That's one of the reasons why people want to keep the complex valued signal. And interesting thing is that this paper shows that if we have cyclostationarity of the discrete time signal from which our vector is taken, then we don't need this augmentation. We just need to do immediately transform to the frequency domain, and just sub-block flipping and conjugation will give us all the information to process. Anyway, that's all for the day. And as I told you, you need to expect second take-home exam probably this weekend. Okay, that's all for the day.